In the last video, we have seen two definitions of inner product. The first definition was fix a basis and take usual dot product. The second definition was the axiomatic one, where we said any function that satisfies those three conditions is called an inner product. Now let's compare these two definitions. The first point is obvious because we work with basis and then we take a tuple, so it works only for finite dimensional vector spaces, but this one works even for infinite dimensional vector spaces. So we already get one advantage here. Now what about finite dimensional vector spaces? So for finite dimension, both the definitions can work. Is it true that definition 1 is stronger than definition 2, or this is stronger, or they're equivalent? Well, it is quite easily seen that definition 1 is at most as strong as definition 2, because if you fix a basis and take dot product, that inner product must satisfy the axioms, because that's how we chose the axioms. We looked at all the properties satisfied by them and then took a subset. So clearly definition 2 is as strong, at least as strong as definition 1. Now what might come as a surprise, and indeed is a bit non-trivial, is that definition 1 and definition 2 are actually equivalent for finite dimensional vector spaces over R. We are not yet in a position to prove it, but let's take a closer look. As an example, we shall work with Rn. First we fix a basis. Now we take two vectors x and y in Rn and we are trying to compute their inner product. So we first express x as a linear combination of the basis vectors. Now we can consider this as a matrix times vector multiplication. The matrix consists of the basis vectors as its columns times the vector of coefficients. Now let's call this matrix the matrix B. It's an n cross n non-singular matrix. So I can very easily work out my alpha vectors as the alpha vector is equal to B inverse of x. Now similarly we can process y to get beta 1 to beta n. These are the coefficients of y when I expand it with respect to the basis, that is B inverse times y. Thus, when I now take dot product of the alphas and the betas, that is compute this, I basically get this transpose times this. Now since I chose any arbitrary basis, so this B is any arbitrary non-singular matrix, so B inverse is also some arbitrary non-singular matrix, and so I say that my dot product is always going to be of the form x transpose then some non-singular matrix transpose times the same non-singular matrix times y, that is of this form. X transpose P, where P is any arbitrary non-singular matrix. Thus, all possible inner products on Rn are of the form X transpose P, y, where P is some arbitrary non-singular matrix. Now this matrix that sits sandwiched between x and y, a matrix which can be expressed as P transpose P for some P non-singular, has a special name. Such matrices are called positive definite or PD. Now we are in a position to state as a theorem the equivalence between definition 1 and definition 2 of inner products for finite dimensional vector spaces over R. We start with V, a finite dimensional vector space over R. Then we take any function from V cross V to R. Then it satisfies the axiomatic definition of inner product if and only if there is a positive definite matrix M such that for all xy in Rn, I have just changed from V to Rn because that makes the statement easier to read. The inner product xy according to this function is actually equal to x transpose that M and y. Now we shall be able to prove this result after we learn about eigenvalues and eigenvectors. But for now, just remember that this theorem shows the equivalence between the two definitions of inner product for a finite dimensional vector space over R, which I have stated here for Rn.